Okay, so last speaker of today is Vladimir Pestov from UFPB and University of Ottawa, and he will speak about the problem of amenability of groups, of paths and loops of finite energy. So, Vladimir.
Thank you, Veriana. Good afternoon to everybody, or good morning. And I want to say that first I met Claudio 32 years ago. It was during my visit to Geneva. But and we have co-authored 4 papers in the 90s when we were all interested in supermanifolds. And I tried and couldn't remember when I met Claudio for the last time, actually. I don't remember when it was. So I have chosen a topic which interests me now and which is sort of close in spirit to mathematical physics. So it's close to the topic of the conference. It's amenability of groups of paths and loops, and more generally groups of maps, various maps. So let me remind that a topological group is amenable if when it acts continuously on a compact space, it admits an invariant probability measure, which is Borel. And in general, we have to add the word regular, but if everything is separable and metrizable, it's automatic regularity. So the problem that motivates this research is a still open question by Alan Carey and Henrik Grünling. They published it in early zeros, but I've heard from them in the last century, this problem. Suppose we have a smooth closed manifold and a compact Lie group, G, is the group of infinitely smooth maps from X to G amenable. And of course, one can generalize to groups of automorphisms of principal G bundles, but I think it will be easy to move there if you know for maps. It has physical motivations, and feel I'm incompetent to talk about those. It's about the existence of an invariant vacuum state for gauge theories. Now, what is known is quite little, actually, up to now. There is a theorem by Paul Maliaven and Marie-Paul Maliaven, which was proved 30 years ago, published 30 years ago, that the groups of continuous paths and continuous loops with values in a compact Lie group are amenable. Even amenability in a bit stronger sense, as I will explain, because beyond locally compact groups, amenability has various meanings. And there is a relatively recent result of mine where I go one step or half step of smoothness up and prove that the groups of Sobolev class 1 loops and paths are not amenable. Amenability, I don't know how to prove, but what I call skew amenable. But this is a version of amenability which is enough to generate invariant states. So I think that might be the right version for this problem. Now, some time I will devote to definitions. So let G be a topological group, a group equipped with a topology making the operations continuous. So we call it amenable if whenever it acts in a compact space, X, it admits a Borel probability measure on Borel sets, which is invariant under the action of the group. Whenever we translate a set A, the measure of this set doesn't change. So the most immediate example of an amenable group is every compact group, because in this case, we can use the Haar measure, the unique invariant, bi-invariant even probability measure on the group. We can choose any point in the space upon which the group acts, the point C, and we just push forward the Haar measure along the orbit map. And this resulting measure will be invariant under the action, which is a fairly obvious argument. So this is the first class of examples, but it cannot be possibly pushed further than this, because there is a theorem which is attributed It's not quite clear who was the first to prove it. It's attributed to Ulam sometimes, or Andre Weil.
Oh, but sorry. Oh, did you pass to the next slide?
Amenable groups is called my slide.
No, we still see the previous one.
Motivation summary, you still see this? Yes, I went to this one. Amenable groups. So, okay, let me escape. Can you now see it now?
Yes.
So maybe I'll just keep it this way without going full screen.
Even full screen, we saw amenable groups.
So it takes a lot of time to update because, all right. Now, the next example, so I repeat the definitions. The next example is every amenable group is, abelian group is amenable because given a finite subset in the group G, in the acting group, we form what is called a Follner set inside the group. We just add this set union with its inverse n times. And one can show that
actually, the image is completely frozen from my point of view. Okay. I don't know if...
yeah, we see there is one moment where we saw it full screen.
What do you see now? Because I exited the full screen.
Yeah, amenable groups, not full screen.
Amenable groups, but I have a few slides. Do you have the definition of a Follner set phi?
No, we see amenable groups.
Still compact groups.
Amenable.
Yeah, but in the second half, what do you see? Phi is equal Follner set. Do you see these words? Follner set.
We do.
Yes.
Yes, then it's the right slide. So we just create those sets with the property that the symmetric difference of this set with its translate by f gets smaller and smaller relative to the set itself in the limit. So we get a limit of counting measures of those empirical measures supported on finite sets, which converges to invariance in the limit. And if we take any accumulation point, any cluster set, point of those empirical probability measures, it will be an invariant mean. So that's basically the whole proof. The details are very easy to restore. Now I'm going to my next slide, still called amenable groups, but it says counterexample free groups. Can you see it?
Yes. Yes, good. I can.
Now, and historically, the theory of amenable groups started probably not with examples, well, with examples of integers due to Banach, and at about the same time, counterexample due to von Neumann, the free group on two generators. Von Neumann was analyzing the Banach-Tarski paradox, and he came to the conclusion that the paradox is due to the non-amenability of the free group on two generators. So I think I will not waste too much time on the proof, but the proof is totally elementary because you take the free group on two generators with discrete topology and you form four sets. G of A, all irreducible words beginning with A. Then G of A minus 1 in the same way, G of B minus 1. And now a very simple calculation shows that your group is a disjoint union of the identity and those four sets. And in particular, now you can pass to the Stone check compactification of the group, which is the compact space upon it acts, the universal compact compactification. It will be the union of those five sets. At the same time, it is the union of translates of G of A and G of B, and of translates of G of A minus 1, G of B minus 1, which contradicts the existence of an invariant measure on this space, obviously, with even additive measure doesn't, finitely additive measure doesn't exist. So it was the example by von Neumann, and basically, I think it's as important for a theory to have counterexamples as examples. It was at the start of the theory. Now, well, this is the picture for Banach-Tarski paradox, which I can skip safely. You can divide a sphere into 5 pieces. 5 is the smallest number. And you can rearrange them as to get 2 identical spheres afterwards. It's just based on this partition that I've shown for the free group. You just do it on every orbit, wherever the action is free. And you are left with a countable set where the action is not free, and you sort of play a trick to hide this countable set as well. So it's quite simple from the modern viewpoint, an explanation, a proof of this. So my next slide is examples of infinite dimensional amenable groups. Is it seen and readable? Perfect.
It's a bit small, but I don't know if you can
Small.
maybe enlarge a bit
I
the
can
window.
go to a window. I don't think it can be done. Oh yeah, it can be done like that.
Okay,
perfect.
way better.
Right. So the theory is has been mostly developed for locally compact groups, but in recent, let's say 20, 30 years, a very interesting development started for what is sometimes called infinite dimensional amenable groups, in a very intuitive sense, infinite dimensional. For instance, the unitary group of the separable Hilbert space in the strong operator topology is amenable. The group of automorphisms of the standard Lebesgue probability space in the coarse topology, the group of permutations of an infinite set, and so on and so on, group of homeomorphisms of the real line. And it has led to some interesting theories in recent times. At the same time, amenability of various groups of diffeomorphisms and groups of smooth maps has not been understood yet. Even for continuous maps, suppose we have a compact space X and a compact group, then is the group of continuous maps from X to G with the uniform convergence topology amenable. It's unknown beyond the unit interval. Already for the square, I think it's unknown. That G is a general compact group, doesn't matter, could be a compact Lie group. It all reduces to the case of Lie groups by the structure theorem. A little bit, let us reformulate the definition of amenability. Suppose your group acts on a compact space X. And so this is a group on my picture. X is a compact space, and the group is acting on it. And suppose we have a continuous function f on this compact space, and a point xi in this compact space. Then we have the orbit map. Every element G of the group is mapped to gxi, right? It's an orbit map from the group to the space. And we can compose the orbit map with the function f. And what can be verified is that this resulting function on the group is what is called right uniformly continuous function. It's uniformly continuous on the right. It means the following, that for every epsilon, we have a neighborhood of identity in the group such that if G H minus 1 belongs to the neighborhood, then the values of the function at G and H differ by less than epsilon. So this is on the right. If you put minus 1 over G, G minus 1H, we got left uniform continuity. And it turns out that every function, right uniformly continuous function on the group, can be obtained this way. And the invariant probability measures correspond, according to the Riesz representation theorem, to positive functionals of norm 1 on the right uniformly continuous functions. So the existence of an invariant measure is equivalent to the existence of a left invariant mean on these spaces. A mean is simply a state, what is known in another context, it's an equivalent notion. It's mean is a linear positive functional of norm 1. That's it. So that's amenability can be reformulated in terms of existence of invariant means on the right uniformly continuous bounded functions. And here are some properties of amenable groups. If we have a dense subgroup of a group G, which is amenable, then the group itself is amenable, and the other way as well. Now, amenability is a three-space property. If you have a normal subgroup and the quotient group are amenable, then the group is amenable. The image under surjective homomorphism, continuous homomorphism, is amenable. And for locally compact groups and locally compact only, a subgroup of an amenable group is amenable. In general, it is not true. In general, it is not true, which makes working in the non-locally compact case much, much more difficult. I will skip this example on this and go to the meat of my talk. So one way to prove the amenability of real line is to, is variance t squared actually should be. 2t squared is, okay. I guess I can call variance t in this case. And sigma squared will be t. So we can take the Gaussian measure. And what happens with the Gaussians as the variance grows, they get more and more flat and spread over the real line. So if we take the Gaussian measure and translate it by a fixed value, let's say x equals 3, then what happens? The two measures, the Gaussian and the Gaussian centered at 3, the translate, they get more and closer to each other. It's sort of visible. And in the limit, one can prove that the total variation distance between them goes to 0. Total variation distance is simply the supremum of differences of all integrals of bounded functions bounded by 1. So this goes to 0. And now if one takes either an outer limit or cluster point in the weak star topology, we get an invariant mean on all, in this case, on all measurable bounded functions on the real line. It's one of the many proofs of amenability of the real line. And of course, the same argument will work for finite dimensional Euclidean space. But which is a product measure, right? And it is defined by the property that for every, whenever take a linear functional norm 1, then the direct image under this functional of the measure is the one-dimensional Gaussian measure, right, in every direction. And the question is, can we define the same thing for L2? But the answer is, as it is well known, negative, because any such measure, if we admit its existence, it's very easy to deduce that the measure of the unit of any ball will be 0. Since L2 is covered by countable many balls, the measure of L2 will be 0. So it's a contradiction. So we need, the situation is a bit like if you want to construct a sigma additive measure on the rational numbers with the property that the measure of an interval is AB is equal to B minus A. It does not exist. So if you want such a measure, we have to beef up Q. We have to replace the rationals with a thicker space, the real line, even in this case. So the Wiener measure has to be supported on a bigger space than L2. For instance, one solution would be to take the countable product of the countable power of the real line and take the infinite product of Gaussian measures. But of course, the problem with this space is it's uninteresting. It's uninteresting from the viewpoint of functional analysis, from the viewpoint of applications. It admits not much structure or infinity. We are more interested in Hilbert spaces and Banach spaces, in some interest in locally convex spaces. But turns out that there are many intermediate spaces between L2 and Rn, talking of the canonical embedding of L2 into Rn, preserving the same coordinates. Intermediate spaces which still have a full measure, full Gaussian measure, this infinite product measure. And the restriction on such spaces will be exactly the Wiener measure. So there is a criterion due to Leonard Gross for a norm on L2 to have the property that if you take the completion of L2 with this norm, its Gaussian measure will be 1, will be full measure. And this criterion is geometric. It roughly tells that the balls of this measure with which we will complete must be thick with regard to the cylindrical Gaussian measures. Basically, essentially the same argument as for L2 will not work. We cannot prove that the balls have measure 0 on null sets. And an example which is important for this talk as well, the classical Wiener space. It's we realize our little L2 as big L2 on 0, 1, square integrable functions on the unit interval, and then we embed it into the space of continuous functions on the unit interval vanishing at 0. That's this 0 means they vanish at the left hand point, and the embedding is just the integration. We take the function and we integrate it from 0 to t. That's the value of the function at t. So we get an absolutely continuous function whose derivative exists almost everywhere, and this square integrable. That's the image of this embedding. It's a proper subspace of C01. And one can show that this, it's not a difficult argument, to show that the Gaussian measure of this space inside R infinity, because it naturally sits inside R infinity as well, is 1. So the restriction of the measure on this space is called the classical Wiener measure. And this is the key for treating the amenability of groups of continuous maps. So I will outline the proof. And we need 2 facts. The first is the Cameron-Martin theorem. Given an abstract Wiener space that is a triple consisting of little L2 and of its completion with regard to a thick measure E, such that this completion has a full Gaussian measure, the translations by elements of this space E, they leave the measure quasi-invariant if and only if those elements belong to L2. So quasi-invariant means that this translation admits a Radon-Nikodym derivative with regard to the Gaussian measure. And so we need this result, and also we need the result that given an abstract Wiener space, every unitary operator or orthogonal operator, if you work with a real case, on L2 extends over the completion, but does not extend at every point. It's not a linear operator. It extends almost everywhere with regard to the Wiener measure. So it is a linear map. It has linearity, but it's only defined almost everywhere, not necessarily at every point. And it leaves the measure invariant. So this Cameron-Martin space, it's a space which directs the measure and determines it completely. And those 2 properties are enough. I will give now a proof of the theorem by Malyevan. It's different from the original proof. I think it's much simpler because the original proof was based on stochastic differential equations. But this proof will be very direct. So slightly more general, just like with the Gaussian measure, we can define a Wiener measure of parameter t of variance, sigma squared. We just do the same construction, but we start with the Gaussian measures of variance t instead of 1. And we still have the same result that it's actually a consequence of the Gaussian case that in the limit, if we start with a Wiener measure and take its translation by a fixed vector of L2, as the parameter goes to infinity, the total variation distance between those 2 measures goes to 0. So asymptotically, the Wiener measures are invariant asymptotically with regard to translations by elements of L2. And they are just invariant with regard to unitary transformations of L2. That's enough. We need to put this together and we get the amenability of the loop groups. Now, so let's suppose, Valeriano, I have 1 hour, 50 minutes, right?
Yeah, 1 hour in principle, so you have half an hour left.
Okay, I don't need half an hour. So suppose we have a compact Lie group with a Lie algebra G. And we realize it's as a subgroup of the group of orthogonal matrices. And then Lie algebra as a group, not group, as an algebra of skew-symmetric matrices. Copy and paste, I guess, suppose, or something. Now we have the joint representation, which under this realization will just the action of by conjugations, and we can fix, because the group is compact, right? There exists on the Lie algebra an invariant inner product. And suppose we now have a function from the interval to the group, which is smooth at a point t. And then we can define the right logarithmic derivative of our function at the point t, which is defined as follows. It is just the usual derivative, but this derivative takes values in the tangent space at the point f of t, f of t. So we move it. We move it back to the origin, to the Lie algebra, by means of f of t minus 1. So the right logarithmic derivative takes values is a function taking values in the Lie algebra. And direct calculation by the definition of derivative shows the following formula, which is very important, that the image of the product of two functions is equal to the first function plus second derivative of the second function upon which we act by the adjoint representation of the first function. So this map, the right logarithmic derivative is a cocycle, right? So if we have a map which is absolutely continuous, then it has a derivative defined almost everywhere with regard to the Lebesgue measure. And so we can form the integral, and this path has finite energy if the integral of the square of the norm of the absolute value exists as finite. Now the map sending such absolutely continuous maps of finite energy to the maps with values in the Lie algebra, square summable maps with values in Lie algebra. It's surjective. And it's an important fact, which is actually specific to dimension 1. It's the source of major problems if you want to pass from the interval to the square. We don't have this property anymore. And this map is surjective, and the inverse is given by the so-called product integral, the multiplicative integral, which I will define now. So suppose we have a step function on the interval, a simple function, taking constant values in the Lie algebra on every interval ti plus 1, every half-open interval. And we have t belonging to the interval tj plus 1, the last interval, right? Not the last one, some interval of the partition. Then the value of the product integral between 0 and t, and this value of t, of our function, is defined as the product of the exponent of, okay, we can start from the right, exponent of t1, the length of the first interval, times the value of the function at 0, and so on and so on and so on, exponent of the length of the interval number j, j minus 1, I suppose, times the value of the function at the point of j minus 1, and so on and so on. And the last term on the left is the length of this partial interval t minus tj, the value of the function of tj. And then we can show that as the mesh of the partition goes to 0, the integral converges. In fact, it converges not only for continuous functions, it converges for L1 functions. It extends by the so-called, there is a Duhamel theorem, which shows that it's continuous with regard to L1 and supreme norm. So there is a convergence for every L1 function. In particular, it makes sense for square integral functions. And whenever we take the square integrable function and, well, L1 function actually, form the product integral, and then look at the logarithmic derivative, then we get the function back almost everywhere. Now this product integral is injective on the paths which take, well, f of 0 equal, I'm not sure, this should not be here, it's just injective on all paths with values in the Lie algebra. And if it's the exact statement is the following, that the image under the product integral gives all the all the paths of finite energy whose value at 0 is identity. That's what we get. So we get instead not all group, but all group of base paths of finite energy. But of course the difference is not big because the group of based paths is co-compact in the group of all paths. So if you prove amenability of one, we get amenability of the other immediately. So it's easy. So the group of based paths, instead of working with this group, we can work with the space L2 of all maps from the interval to the Lie algebra. But the group operation now becomes as follows. We can lift it up, the group operation. It becomes the product of f and g. It becomes f plus g, upon which we act by the joint representation with the image of f under the product integral. So this is the new group operation. And it's very convenient to work with this operation because it's easiest to be mysterious. It is made up of shifts and unit and a joint representation, shifts and unitary operators. So it's an affine isometry. We have realized our group as the group of affine isometries, in particular the Hilbert space. And we remember that the Wiener measure is asymptotically invariant under shifts and invariant under unitary operators. So it's almost clear. Intuitively, at least, technically it's still difficult, but intuitively it's clear how to get amenability. Now, so back to the groups of maps. We have a compact Lie group G, and we have this group of paths of finite energy, or equivalently of all maps of Sobolev class H1, which is dense. It's easy to see it's dense because even C-infinity maps are dense, and this is bigger. And we realize it as L2, as we just said, is group of L2 maps with values in G with this specific new multiplication. And we have the product integral, which is a group isomorphism. So thanks to the product integral, we can forget about the group of maps with values in G. We can just stay upstairs, look at the L2 maps with values in the Lie algebra. Now, the Wiener measures of parameter T exist on the groups of continuous maps with values in G. And it's basically the classical Wiener measure, right? Because this space is just the space of continuous functions in 0, 1 tensored with a finite dimensional Lie algebra. And we have this immersion, the same formula. Given such a map, we send it to the integral from 0 to t. And takes a completion with a certain weaker norm of this space. Now, we can define the action of our group on the space of continuous maps with values in the Lie algebra by the same formula exactly. It's a shift plus shift of the first function plus the second function upon which we act by the unitary operator. Because remember, the unitary operator on L2, it extends almost everywhere to an operator on the completion on the continuous functions. And the measures are invariant under rotation, asymptotically invariant under translations, which means that there is an invariant mean on all bounded Borel functions on continuous function of Ig, which is invariant under the action of our group. So we have to push it down to our group of continuous maps, because the product integral only establishes an isomorphism between the group of L2 maps and our group H1. But this group is bigger, and our embedding, the group of continuous maps, is bigger. And this is done with the help of the so-called Ito map. So the product integral, the product, not map, the product integral extends to a map which commutes with the action of our group of finite energy, and is defined almost everywhere. So how it is being done? So just a very quick. I will write down a formula. So this is a formula for the product integral for step functions. It is the product of exponentials of t minus tj, f of tj, exponential of the length of the next interval times of the value of a function, exponential of the length of the first interval, the value of the function 0. Now, we need to extend it over the completion, but intuitively it corresponds to what? Because to go from the space of subspace of Sobolev class 1 functions to L2, we need to differentiate, right? Or if we start with L2 directly, we have to integrate. Gosh, this formula I wrote, now it's wrong. The formula is wrong because here I should put, it goes in the wrong direction. It goes in the wrong direction. I mean, it has to, okay, so forget about it. Forget this formula, and I should have written in the other direction. The idea is the following, that if you want to extend it, then we are extending from the integral. We take the integral of the function, then we apply this formula, or we can go in one step. Go in one step means this. The formula for the Ito integral, it's an Ito map. It's an approximation of the product of exponentials, but this time not the length of the interval times the value, but value of the function at one endpoint minus at the other point. So the function has already been integrated one time, times the exponential difference of the values of the function, and so on, and the exponential of the value of the function at the first point. And this limit, as the mesh goes to infinity, to 0, one can check it's defined. It's not defined for all continuous functions. It's everywhere discontinuous. But it's defined for all Helder functions of exponent alpha, which is bigger than 1/3. So sufficiently large. And at the same time, such functions with exponent less than 1/2, they support the Wiener measure. So there is a window between 1/3 and 1/2 where still the Wiener measure exists. Almost every function has this property, and for almost every function, it means the Ito map is well defined. It converges. So we have an equivariant map from the space of continuous maps with values in the Lie algebra to the space of continuous maps with values in the Lie group. And we push down the Wiener measure. We get what's called nonlinear Wiener measure in this case, and we get an invariant mean on continuous function with values in G. And we get a little bit more than amenability. We get an invariant mean, left invariant mean on bounded Borel functions, all bounded Borel functions. But it's not invariant under all elements of the group, but only of a dense subgroup, H1. But in particular, from here, one deduces easily the usual amenability, the existence of a left invariant mean on a much smaller space of the right uniformly continuous functions. It will be invariant with regard to every action. And there are big difficulties if we try to extend the argument either to, well, at least I'm having difficulties, either to high degrees of smoothness, or I already don't know, as I said, if the group H1 of finite energy paths and loops is there, if they're amenable or not, or high dimensional X. And the transition to loop groups is easy from here. I will not talk about it. because the formula for multiplication becomes more complicated. It requires higher order terms, and the most obvious choice of Wiener measures of growing parameter, they are no longer asymptotically invariant under those. So it's not quite, doesn't seem to be an obvious way to extend this argument. But now let me say a few words, just 3 or 4 slides, about my recent result. Instead of the Wiener measure, because the Wiener measure is a limit of Gaussians, right? So one can use Gaussian measures, finite dimensional, of course, or else equivalently one can use the product of Haar measures on spheres of high dimension. They are almost the same in some sense. And it turns it in some regard, it's gives better result in some way, because you don't need to take the completion. You see, the problem with this argument in the previous Malevin is your measure doesn't live on your group, it lives on a bigger secret group. So you can only conclude the amenability of a bigger group, which is a low degree of smoothness, right? Not so nice. But if you work with Gaussian measures, finite dimensional, you still stay inside the group itself. You get less, you don't get means on Borel functions, on all measurable functions, but you get a property which is similar to amenability. So basically my sequence of measures will be just as follows. I partition my interval into n subintervals, and I take subspace of simple functions in L2, in the space of L2 with values in the Lie algebra. And either Gaussian or a sphere of high dimension, it doesn't matter, the same argument. And then I both send the mesh of the partition to infinity, and I send the parameter of the Gaussian measure, so the radius of the sphere, to infinity. And what happens, I get asymptotic invariance, but not for all measurable functions. So the argument becomes quite a bit trickier, because you need to use the concentration measure considerations at some points. It's different argument anyway. But we conclude that there is a left invariant mean on bounded left invariant with regard to that operation lifted upstairs on bounded uniformly continuous functions on this L2. But uniformly continuous on L2 means, from the viewpoint of the groups, left uniformly continuous structure on the group, because it's invariant with regard to left translation. So it is the so-called left uniformly continuous structure, not the right. To get amenability, you need the right. So I was very spent a lot of time. Basically, I gave this argument up because I thought it was not the right result. But then I realized slowly that it's good what you get. So we have an invariant mean on the left uniformly continuous functions, which is, Martin Schneider has suggested this name, skew amenability. It's kind of a amenability from on the other side. And then I realized it's exactly the version of amenability that is needed to construct invariant states. Because you see, for locally compact groups, it's the same thing. Skew amenability is equivalent to amenability. It's an old result, well known. But for those groups, no, it doesn't seem to be the same. For this group, I don't know exactly yet, but for other groups, so the unitary groups, it's amenable, but not skew amenable, and so on. And that's basically the last mathematical slide. Suppose we have a strongly continuous unitary representation of a group, of the topological group. And on the space of representation, so we have the space of bounded operators, linear operators, the algebra, and we have a state phi on this algebra, a positive linear functional norm 1, and it's called invariant under the representation pi if it has this property phi of the conjugation of t by an element of the group is equal to phi of t for every bounded operator T and every element of the group. Then we say its status is invariant. And a unitary representation which admits an invariant state is called amenable in the sense of Becker, of Bashir Becker, who has developed a theory based on some previous results of Kohn. And with Thierry Giordano, we remarked some years ago that if we have not in those terms, at that time, the notion of a skew amenable topological group did not exist, but essentially we stated and proved this result, that every strongly continuous unitary representation of a skew amenable topological group admits an invariant state. And that's probably what is needed. I still would like to discuss it with Alan and Henrik if this is what they really meant. But I suspect the real conjecture that every unitary representation of the group C infinity maps from a smooth manifold to a compact Lie group admits an invariant state, right? For that you need skew amenability. So here is my my paper from 2020, and where you can find everything. And so buon compleanno, tanti auguri, Claudio. That's it. I'm done.
Thank you.
Thank you, Boba.
Thank you.
So is there any comment, any question?
When you say a smooth manifold is without boundary or with boundary, possibly?
They meant probably without boundary.
Because an interesting case would be the case of the unitary disk in the complex plane.
Yeah, definitely it should be addressed. For the moment, I haven't
because
thought much about this.
In this way, you get a lot of example, because you can quotient for any fine discrete group acting on the disk. You get some subgroup, and so you get essentially some weaker version of amenability for loop groups over Riemann surfaces of genus greater than 1.
I have a feeling that if the result is true, it should be true for both, with boundary and without. That's because look at the paths and loops, right? Because they're more or less equivalent. Paths have boundary, loops don't, but the result follows from each other. So I think it would be the same probably in the general case.
Yeah, but you can see, I mean, function on C1 is periodic function on the interval, in some sense.
Right. I agree. Yeah. Of course, there are very subtle things. That's true. To the image, yeah. So basically, a non-stanza would be, I don't know. I forgot what they meant. But the question is open for every case, for boundary, without boundary.
So thank you for this beautiful talk and for your wishes as well. Thanks.
Any other question on the mic? Okay, so let's thank Vladimir again for his talk.
Thank you.
So I will stop the recording now.